For a delta-connected load, the current in each phase is equal to the load current divided by the square root of 3. To calculate the load current, divide the power in watts by the voltage. In this case with 5000 watts and 480 volts, the load current is 5000 watts divided by 480 volts, which equals 10.42 amps. Therefore, the three-phase load current is 10.42 amps divided by the square root of 3, which equals approximately 18.1 amps. The type of load, whether it's resistive or inductive, does not affect the calculation of the three-phase load current in a delta configuration. Delta connections are inherently balanced, meaning that the load current is evenly distributed among the three phases. This characteristic holds true regardless of the nature of the load connected in the delta configuration. In summary, the three-phase load current for three 480 volts 5000 watt resistive heaters connected in a delta configuration is 18.1 amps. To further clarify, let's delve into the details of delta connections and three-phase power systems. A three-phase power system consists of three alternating current AC voltages that are out of phase with each other by 120 electrical degrees. These three phases are typically labeled as A, B, and C, or sometimes as 1, 2, and 3. There are two common ways to connect these phases to a load, which are delta and Y, sometimes spelled Y. In a delta connection, the three phases are connected in a closed loop, forming a triangle, which resembles the Greek letter delta. Each corner of the triangle represents a connection point to the load. The voltage between any two phases in a delta connection is the line voltage, which is the voltage supplied by the power source, in this case 480 volts. The current flowing in each phase winding is the phase current, and the current flowing in the lines connecting the delta to the power source is the line current. The relationship between phase current and line current in a delta connection is that the line current is equal to the square root of 3 times the phase current. A resistive load is one that consumes electrical power and converts it into heat, light, or other forms of energy without storing any energy. Examples of resistive loads include heaters, incandescent light bulbs, and electric ovens. An inductive load, on the other hand, is one that stores energy in a magnetic field. Examples of inductive loads include motors, transformers, and solenoids. Inductive loads cause the current to lag behind the voltage, creating a phase difference between them. This phase difference is measured by the power factor, which is the cosine of the angle between the voltage and current. A purely resistive load has a power factor of 1, while an inductive load has a power factor less than 1. In a balanced three-phase system, the loads on each phase are equal. This means that the voltage, current, and power factor are the same for each phase. When a delta connection is balanced, the current is evenly distributed among the three phases regardless of whether the load is resistive or inductive. The reason why the type of load doesn't affect the calculation of the three-phase load current in a balanced delta configuration is that the phase angle between voltage and current is the same for all three phases. This means that the power factor is the same for all three phases, and the total power consumed by the load is simply 3 times the power consumed by one phase. To calculate the three-phase load current, you need to know the total power consumed by the load and the line voltage. The formula for calculating the three-phase load current in a balanced delta configuration is line current equals total power divided by the square root of 3 times the line voltage times the power factor. In the case of purely resistive heaters, the power factor is 1, so the formula simplifies to line current equals total power divided by the square root of 3 times the line voltage. For the given example of 3 480 volts 5000 watt resistive heaters connected in a delta configuration, the total power is 3 times 5000 watts, which equals 15,000 watts. The line voltage is 480 volts. Therefore, the three-phase load current is 15,000 watts divided by the square root of 3 times 480 volts, which equals approximately 18.1 amps. It is crucial to ensure that the three-phase contactor and breaker in the industrial control panel are properly sized to handle this current. The contactor should have a current rating that is greater than or equal to the calculated load current of 18.1 amps, and the breaker should have a trip current that is also greater than or equal to 18.1 amps. It is also important to consider any directing factors that may apply to the contactor and breaker, such as ambient temperature and altitude. In addition to the current rating, the contactor and breaker should also have a voltage rating that is greater than or equal to the line voltage of 480 volts. The interrupting rating of the breaker should also be sufficient to handle the available fault current at the installation location. Proper wiring practices are also essential for ensuring the safe and reliable operation of the three-phase system. The conductors should be sized appropriately for the load current, and they should be protected from overcurrents and short circuits. The wiring should also be installed in accordance with all applicable codes and standards, such as the National Electrical Code, or NEC. Grounding is another important aspect of three-phase power systems. The system should be properly grounded to provide a low impedance path for fault currents to return to the source. This helps to protect personnel from electric shock and to prevent damage to equipment. The grounding electrode conductor should be sized in accordance with the NEC, and it should be connected to a suitable grounding electrode, such as a ground rod or a metal water pipe. In summary, calculating the three-phase load current for a delta-connected load involves dividing the power by the voltage and then dividing the result by the square root of 3. The type of load, whether it's resistive or inductive, does not affect the calculation in a balanced delta configuration. Proper sizing of the contactor, breaker, conductors, and grounding system is essential for ensuring the safe and reliable operation of the three-phase system. Understanding the fundamentals of three-phase power systems and delta connections is crucial for electrical engineers and electricians who work with industrial control panels and other three-phase equipment. The calculations presented here assume a balanced system. In cases where the loads are unbalanced, more complex calculations are required, often involving symmetrical components analysis. Symmetrical components break down an unbalanced three-phase system into three balanced systems: positive, negative, and zero sequence, which can then be analyzed individually and recombined to determine the actual currents and voltages in each phase. Furthermore, harmonic distortion can also affect the current in a three-phase system. Harmonics are sinusoidal voltages or currents that are integer multiples of the fundamental frequency, which is typically 50 Hz or 60 Hz. Harmonics can be generated by nonlinear loads such as variable frequency drives, electronic ballasts, and switching power supplies. Harmonics can cause increased heating in conductors, transformers, and other equipment, as well as voltage distortion and interference with communication systems. To mitigate the effects of harmonics, harmonic filters can be installed to reduce the harmonic content of the current. These filters typically consist of capacitors and inductors that are tuned to specific harmonic frequencies. Power quality meters can be used to measure the harmonic content of the current and voltage in a three-phase system. These meters can provide valuable information for troubleshooting power quality problems and designing harmonic filters. When working with three-phase power systems, it is essential to follow all safety precautions and to use appropriate personal protective equipment, or PP. This includes wearing safety glasses, gloves, and insulated tools. It is also important to de-energize the equipment before working on it and to verify that it is de-energized using a voltage tester. Lockout-tagout procedures should be followed to prevent accidental energization of the equipment. Regular maintenance and inspection of three-phase power systems are also important for ensuring their safe and reliable operation. This includes checking the tightness of connections, inspecting conductors for damage, and testing protective devices. Any problems that are identified should be corrected promptly to prevent further damage or safety hazards. The NEC provides detailed requirements for the installation and maintenance of three-phase power systems. It is important to be familiar with these requirements and to follow them carefully. The NEC covers topics such as conductor sizing, overcurrent protection, grounding, and wiring methods. In addition to the NEC, there may be other applicable codes and standards such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is important to be aware of these codes and standards and to comply with them. Continuing education is also essential for electrical engineers and electricians who work with three-phase power systems. New technologies and techniques are constantly being developed, and it is important to stay up to date with the latest advances. There are many training courses and seminars available on three-phase power systems and related topics. These courses can help to improve your knowledge and skills and to ensure that you are working safely and effectively. Remember that while the calculations discussed provide a solid foundation, real-world applications may present complexities. Factors such as cable impedance, transformer impedance, and motor starting currents can influence the actual current flow in the system. Therefore, it is always best to consult with a qualified electrical engineer for detailed system design and analysis, especially for large or critical installations. Always prioritize safety when working with electrical systems. Ensure proper grounding, use appropriate personal protective equipment, and follow established lockout-tagout procedures to prevent electrical shocks and arc flash hazards. By adhering to these safety practices, you can minimize the risk of accidents and ensure a safe working environment. Furthermore, remember that local electrical codes and regulations may vary. Always check with the local authorities to ensure compliance with all applicable requirements. This may involve obtaining permits, submitting drawings for review, and undergoing inspections. Compliance with local regulations is essential for ensuring the safety and legality of your electrical installations. Keep in mind that the information provided here is for educational purposes only and should not be considered a substitute for professional engineering advice. If you have specific questions or concerns about your electrical system, it is always best to consult with a qualified electrical engineer. They can assess your specific situation and provide tailored recommendations to meet your needs. To summarize, remember the following key points. Firstly, for balanced delta-connected load, the line current is equal to the phase current multiplied by the square root of 3. Secondly, the type of load, whether resistive or inductive, does not affect the calculation of the three-phase load current in a balanced delta configuration. Thirdly, proper sizing of the contactor, breaker, conductors, and grounding system is essential for ensuring the safe and reliable operation of the three-phase system. Fourthly, always follow safety precautions and use appropriate personal protective equipment when working with electrical systems. Fifthly, comply with all applicable codes and standards, including the NEC and local regulations. Sixthly, consult with a qualified electrical engineer for detailed system design and analysis, especially for large or critical installations.